When browsing through the over 300 videos on my YouTube channel, what do you think is the most dangerous topic? For me, it is for one definitely working with mains voltage, since I did an experiment before in which just 20 volts AC was very hard for me to endure. And the other thing are lithium polymer batteries, or LiPo batteries, which can expand, explode, start a fire and whatnot if they are not handled correctly. Probably the most difficult task is charging them correctly, with a constant current, constant voltage method. In my example, this LiPo battery here comes with a capacity of 600 mAh. So to keep it safe, we should charge it with a constant current of around 300 mA and up to a voltage of 4.2 volts, like it is common for 3.7 volt LiPo batteries. A safe way to do this is to either use a pre-made LiPo charging board, whose current set resistor you will have to change, or you make your own like I did right here around a specialized IC, which is made for such tasks and thus pretty safe. But you do not care about safety, and thus instead searched for LiPo charger schematics on Google Images, and found a few which only required a handful of components. Perfect! And you're in luck, because in this episode of testing circuits I found on the internet, I will test the two schematics you picked out to be your LiPo charger, and show you what flaws they come with and how we can maybe improve them. Let's get started! This video is sponsored by Altium. I recently switched over to the Altium Designer software and used it to create a couple of PCBs. And what I can say is that it might take a bit of time to get used to, but the software offers pretty much everything you could ever need to design a professional PCB. So feel free to test the Altium Designer by yourself by following the link in the video description. First off, let's talk in detail about this constant current, constant voltage charging method by looking at this lovely handmade diagram. As you can see, the battery voltage is pretty low at first, with around 3.5 volts. Now hooking this battery up to a constant voltage of 4.2 volts, which is the end battery voltage we aim for, would result in a huge charging current flow which our battery might not be able to endure and thus get destroyed. That is why we have to limit the current to a value which our battery can handle, which is commonly known as a constant current limit. This charging limit can always be found in the datasheet of the battery, along with other useful information on how to charge it. But in my case, my battery did not come with a datasheet, and thus I kept it safe by choosing a charging current half of its capacity. Now with the constant current function pumping current into the battery, its voltage obviously rises. And as soon as it reaches 4.2 volts, the current falls underneath the constant current limits, and thus we enter the constant voltage mode, at which point the battery charges up to its max capacity, where almost no current is flowing anymore. And this is how to properly charge a LiPo battery. But what circuit could do such a job? Well, you firstly chose this circuit right here, that you found on the website Donut Science. A great name, by the way. The first two sentences say that the regulator sets the required top voltage and the in-series resistor limits the maximum current. So without thinking about how this circuit might function, I simply built it up on the breadboard according to my own redrawn schematic, in which I used a 200 ohm trimmer instead of a 100 one, because I didn't have one laying around. That did not really matter though, because after powering the circuit with a minimum of 6 volts, like it was recommended, I tried adjusting the trimmer in order to reach 4.2 volts on the outputs. But surprise surprise, I was never able to reach 4.2 volts. The maximum was around 3.7 volts. And no, my trimmer was not the culprit. but we can find the problem by investigating the LM317 adjustable regulator, which is being used as an adjustable voltage regulator. Now of course we could go through the 32 pages of its datasheet in order to find out how it functions and how to calculate all the values for complementary components. But let me tell you that all you need to know for basic calculations is that the voltage difference between outputs and adjusts will always be 1.25 volts. That means that there will be a voltage drop of 1.25 volts across this 220 ohm resistor, and the current flowing through it will be approximately the same as the current flowing through the resistors below, if we ignore the itsy bitsy tiny current flow from the adjust pin. This way, this is basically just a voltage divider, which means that by using this simple formula, we get an output voltage of around 3.63 volts across all resistors, which is around the same value as we measured. And the original trimmer value of 100 ohm would have even decreased the output voltage to 3.07 volts. So to increase the output voltage, we simply have to increase the lower resistor value to something like 470 ohm, which should give us a maximum output voltage of 5.05 volts. And as you can see, by changing the resistor, I was finally able to adjust the voltage to 4.2 volts. But I feel like connecting the battery now would be a mistake, because with the resistor value of 1.2 ohm, there would be a theoretical short circuit current of 3.5 amps. And even the Donut Science website states a current of 1 amp, which is too high. So I firstly tried a resistance of 14 ohm, with short circuit current of 300 milliamps. But as you can see, a LiPo battery is not a short circuit, and thus the charge current was way too low. So I switched back to the 1.2 ohm value, which limited the current to a suitable value. But you know, I should have somehow doubted the website's information as soon as I read that a higher resistance will equal a higher current flow. But anyway, as you can see, the battery now charges just fine, but while its voltage rises, its current flow decreases. The reason is that this resistor current limiting method is not a constant current method. The battery, however, does reach its end voltage safely. It only takes a bit longer. So overall, while this circuit came with small mistakes, it works pretty decently and is kind of safe. Next, you had a look at this a bit more complex LiPo charger based around an operational amplifier. So once again, without thinking about how the circuit works, I built it up on a breadboard. And after hooking the battery up in its rightful place, it seems like it was charging without a problem, but the current flow was a bit low. So just like before, it was time to change the resistor value, to this time around 10 ohms, since we're dealing with 9 volts as the charging voltage here, which resulted in a current flow of around 300 milliamps. You might be thinking that 9 volts sounds dangerous around a 4.2 volt battery, and you would be absolutely correct. But there's a trick the circuit uses, because the utilized OpAmp acts as a comparator. Its inverting input is connected to the battery voltage, and its non-inverting input is connected to a voltage divider, which creates around 3.55 volts. So when the battery voltage is underneath around 4.1 volts, then the non-inverting input features a higher voltage than the inverting inputs, and thus the output turns on. The charging LED lights up, and the transistor lets the battery charge. But when the battery reaches above around 4.1 volts, then the inverting input is higher than the non-inverting, and thus the output turns off and the charging is over. The text from the website Circuits Today, where the circuit originated from, describes the theory like this as well, and overall it sounds promising. But there is a small problem. Practically speaking, the LiPo battery voltage drops as soon as the charging current is cut, and thus this circuit output oscillates quite a bit while reaching the charging stop voltage, which I think is acceptable for the battery, but certainly not perfect. Also, the charging current is still limited by a resistor and is not a constant current source, which means that this circuit is not really better than the first one. So hold my beer while I draw up a super simple constant current, constant voltage source, which might be horrible inefficient, but pretty safe. As you can see, I'm using two LM317 regulators. The first one basically sets the maximum constant current, which we can calculate by once again using the known reference voltage. In my case, I used a 4 ohm resistor. And the second LM317 regulator basically sets the constant voltage with pretty much the same circuit setup as we have seen it before. This time though, I didn't feel like testing this circuit on a breadboard, and thus instead soldered all of the components together in mid-air. After then adjusting the output voltage to 4.2 volts, it was time to hook up the LiPo battery, which, as you can see, started charging with a constant current of around 300 milliamps. The current flow did drop however, since the regulators were getting quite hot. But nevertheless, the constant current, constant voltage charging methods did work perfectly fine until the end. And of course, we could make this circuit even safer by monitoring the voltage and current with a microcontroller and maybe even adding a MOSFET emergency shut-off switch like I did right here. But overall, I would still not recommend such a solution. Instead, do me a favor and only use a proper lab bench power supply, or a specialized LiPo charger, or even a more expensive multiple battery type charger in order to safely charge your LiPo batteries. But nevertheless, I was still happily surprised to see that most of the designs I found on Google Images were pretty safe when it comes to LiPo charging. But it is still always important to understand how a circuit works before using it. And with that being said, thanks for watching. As always, don't forget to like, share, subscribe and hit the notification bell. Stay creative and I will see you next time!